what we're going to talk about today for 3 hours is an extension of what we started talking about last week, which is the reservoir rate equation, but the steady state or pseudo-steady state reservoir rate equation. And I had asked you to read the paper by Mike Vetkovich. Everybody who read it, there we go, a couple of you. He touches in the paper upon the idea of using something other than log RERW that we talked about in the denominator of the reservoir rate equation with something else. Did anybody catch that? Because we hadn't really talked about it, so that's okay. And we also, last week, when we talked about the reservoir rate equation, we talked about it for a radial well, a radial cylindrical geometry with a wellbore radius, RW, and an external no-flow outer boundary at a distance, RE. And we were talking about, as we will continue next week and the rest of the course, about gas flow, single-phase gas flow. Okay? And we talked about the use of the pseudo pressure function in the reservoir gas rate equation. So I'll just rewrite that equation and we'll start with that. And we had a constant, which I'm not going to carry through on all of this. I might come back to it for my set of units. But basically we had this KH, and then we had the driving potential was the pseudo pressure at average volumetric reservoir pressure minus the pseudo pressure at the bottomal flowing conditions, like that. And then there was reservoir temperature down here, and I think all that was left was the log of RERW, and because we're using average reservoir pressure and no flow outer boundary, we had a term minus 3/4. And then we had also talked about skin, right? And then this pseudo pressure we had defined as the 2, and I told you why that was defined that way, as P over mu Z, which is effectively rho over mu dP. I think that was it. So this is in standard volumes per day, so it would be like standard cubic feet per day. And yeah, it's derived from Darcy's law. Any questions about this? This is pretty much what we did last week. Okay. So, and this is for what we call pseudo-steady state flow. Okay, with an outer boundary that has no flow outer boundary. I'll just write no flow outer boundary. Like that. And what do we mean by steady state? It means that everywhere within this this flow unit, this flow volume, from RW, basically we've got a well bore. I'll try to sketch it here without too much thickness out to here. This is RE. This is from the center of the well out to there, and then this distance here is RW, wellbore radius, and we've got no flow at the outer boundary. I'm just going to take, it's 360 degrees around. I'm just going to give you a section of about 30 degrees. It's actually going all the way around. the whole way if it's draining a total volume. And what the steady state means is that if you look anywhere inside the reservoir, at any distance, at any radius, here or here, or at near the well bore, doesn't really matter. Basically, you have the same mass flux. Okay, the mass flux is constant. Okay, and that's everywhere except at the boundary, because at the boundaries there's no mass flux coming in. Otherwise, in the rest of the reservoir, you've got the mass fluxes. So it's a steady state in that sense. So we're draining from the outermost part of the reservoir flowing in. You're draining from this part of the reservoir. You're draining from everywhere. Okay? Everybody is contributing to the rate. Okay? It's kind of like what's being taken out of the well is the same flux that's kind of moving around everywhere else. Okay? So that's the pseudo-steady state condition. And if you change the flowing bottom hole pressure at this point here, then you will, if you can maintain pseudo-steady state, if you change that, this is what we talked about having control over. This is what we have control over today. This is about the only thing we can do anything about. We change that pressure and we get a different rate. And the assumption with this equation is that if we change it right now, the entire drainage area from RW to RE reacts immediately to give us what we want. Okay? So if we change it, the rate's going to be larger at the wellbore, it's going to be larger everywhere, or smaller, depending on how we change PWF. Okay? That's the way it's working. As things change in time, whoa, that didn't work very well. As things change in time, for a given bottom hole flowing pressure, we're going to get less and less rate, right? We make 1,000 barrels per day today. We're not going to make 1,000, well, this is gas rate, 1,000,000 cubic meters per day today. In a year from now, we won't be making, if you keep everything constant on the right side, PWF, which we can control, KH is not going to change, temperature, log RERW, draining the same volume. In a year, we're not going to make the same rate. Why not? Why not? Something has to change if we get less rate. What is the function of time here? Okay, so if we fix PWF, the rate will be a function of time, and it's going to go down. Sorry, that's the way it is. Why is it going to go down? What is changing as a function of time? The reservoir pressure. This thing here is a function of time. Because you deplete the material balance. We're going to be talking about that, but that's what happens. You take something out, the pressure goes down. So the average pressure is going down. That is why you get the transient rate behavior. Okay, transient means function of time. Well, okay, time dependence of rate. So are there any questions about that? That's what this is saying. And if the permeability is high enough for a gas well, let's say greater than about a millidarcy, then if you change the pressure at the bottom of the well by changing the choke at the top, it'll take within a day, maybe a week at the most, but within a relatively short amount of time, probably a day or just hours, the entire drainage volume will be into a new pseudo-steady state, a new state with a different bottom hole flowing pressure, and it'll give you a new rate. It happens quickly, okay? But if the pressure's low enough, and what's low and what's high, it's like what's a big salary? You can ask Helgelund. You know, he now knows what a really big salary is. Okay, as opposed to the used to be pretty big salary. Okay, what is low enough permeability that it might take weeks or months or even years, if you change that bottom hole flowing pressure, for it to really be felt by this outer boundary, okay, before it really affects the outer boundary. Okay, well, at a low enough permeability, it takes a long time for that pseudo steady state to kind of be a good assumption. Okay? It doesn't happen instantaneously. It just doesn't. It takes time. But the relative amount of time in the old days, let's say in the 60s and 70s, 60s for sure and before, permeabilities were every year high enough that it happened in such a short time that most of the engineering was done on that assumption, unless you looked at very short time spans of 12 hours or a day. So what we're going to talk about today, and normally we don't do this in the class here, is what about that period it takes before the outer boundary feels what's going on at the wellbore. Okay? That's what we're going to talk about today. And in general, and before that happens, the well is behaving as if it's in an empty, an infinite reservoir. Okay? Because it doesn't know there's the boundary. It hasn't reached the outer boundary. Okay. So the analogy I want you to kind of do is that, let's say that we've got this, you're up in the mountains in Norway, and you've got this pond or a small lake, okay? And you throw a big chunk of rock in the middle of the lake, right? Okay? And it goes splash, okay? And then you know it's going to create a ripple, right? And that ripple is going to move outwards with time until finally it hits the boundary of the lake, right? Takes some time. Might take a few seconds or a few minutes, depends how big the lake is. But if you do the same thing in the ocean, right? It might be, depending where you are in the ocean, it might take a while before one of those ripples hits the continent. Okay? So we're talking about that time from when you do something at the innermost area until you reach the outer boundary. And that is basically, this period of time is typically referred to as the transient time before pseudo-steady state kicks in. So transient, it's not really a good name because even what we were talking about, pseudo-steady state, transient means as a function of time. But in petroleum engineering, it used to mean this period used to mean before reaching pseudo-steady state. Okay? And what they would do is that they would usually produce a well, and then they would study how the bottom hole flowing pressure for a constant rate changed as a function of time during that period. So that's a field of engineering. So we've got this, and we don't really call this pseudo-steady state anymore. This is old school. Okay, it's now called boundary dominated. Okay, boundary dominated. Okay, it's the same thing. Boundary dominated flow. And before you reach that, the well actually thinks it's in an infinite reservoir. Okay? And so this transient here, before reaching boundary dominated, is referred to as infinite acting. Okay? Infinite acting. It's as if, as far as it knows, RE is infinite. Okay? Well, that's not really a good thing. I'm not going to write it that way. That's not a good way but it's like there is no RE. Okay? But if we look at our experiment in the pond, if you consider that ripple that it creates, that first ripple as the wave moving outwards, okay, it's affected that far. So however far that's gone out, that's kind of our current RE, okay? And the same thing happens for the well, is that after 1 hour, it's really affecting, let's say, what do we mean by affecting? Okay, if we start producing this well, after 1 hour, let's say that a 1 millibar pressure drop is important, or 1 psi, whatever you want to pick. If you say that if the pressure drop at some radius is greater than some epsilon, it might be a millibar, or it might be 1 psi, or whatever you want to pick as significant, okay? That it takes 1 hour for the pressure drop at this radius to drop 1 millibar, okay? Now, at 1 minute, it had dropped 0.001 millibar, but we don't consider that important. So it's kind of an arbitrary definition, but we have to make this definition in order to talk about drainage effect. Okay, so we say at 1 hour it's been affected there, and then at 24 hours, 1 day, out at this distance here, it's now the pressure drop is dropped 1 millibar at this point. Okay, and then at 10 days it's here, and then finally when it reaches is out here, maybe it's 30 days, and that would be what we call the time to pseudo steady state. I don't know what they call it now, boundary dominated time. I don't know what the nomenclature is. Time to become boundary dominated, something like that. Okay, it took 30 days in this particular well. So we're going to talk about the behavior of the well from 0 to 30 days during these 3 hours. Because once you reach 30 days, we can kind of use this equation up here. Okay? As long as you just keep it on a fixed rate or fixed bottom hole pressure. Kind of don't change the system. Now, there's something called well testing. I'm just, because you guys are new to this whole area, something we used to call well testing. It gradually became known as pressure transient analysis. Maybe that's what it's still called. We have a graduate student from University of Calgary. Hamid here is with us. He's doing his PhD on pressure transient. Actually, maybe not pressure transient analysis, but that's what his professor calls it. Pressure transient analysis. Okay. And that generally is an area where you generally assume that the rate is a constant or controlled. Okay, you control the rate, and you study how the pressure in the bottom of the well varies as a function of time. I can't write PW because last week I introduced PW as being a pressure up at the top, so I don't want to confuse you. Okay, I'm just going to say, let's say the well is flowing, so it's the flowing bottom hole pressure, how it varies with time. So the basic assumption is that this is constant or controlled. We study how the bottom hole pressure changes with time, and from that study we're able to estimate permeability primarily. That's the most important number you're looking for. Possibly this skin factor we talked quite a bit about last Thursday. The magnitude of that, if it was 2 or 8. Remember what 8 was? 8 was an important number because you're now producing half the rate as if you didn't have skin. Right? And the current average reservoir pressure. If you shut the well in and you use this analysis, now in that case you have two rates. You have the rate when it's flowing and you control it, shut it in, okay, and you see how the pressure changes. And then you're able to estimate permeability, skin, and average pressure. Okay? Okay. And then if you're really good at this, you can maybe estimate other stuff too. But it becomes a little bit non-unique. You think you might be able to establish something or another, or you might be able to establish, for example, how big is RE? Okay, how big is the drainage area? What's the shape of the drainage area? Remember we talked last week about the fact that we don't drain circular volumes, but they have different weird shapes. Okay, you might be able to come up with the shape, and so forth. There's a bunch of things you can try to come up with. Now, how this is done. I want to try to get through this, how this is done, just in approximately. Well, we start with the same equation, okay? But we make a couple of changes. Now, I'm going to leave gas for the time being because if you use pseudo pressure, then it's the same as really treating a single phase oil. I mean, it's behaving kind of like you make it behave like a single phase oil. So, but I'm going to talk about single phase and what we typically used to call slightly and constant compressibility, compressible systems. Okay? Okay? If you set up the differential equations describing flow, which combines the Darcy equation with the material balance in a differential form, then you getting pressure here. But now we're not going to use average volumetric pressure because we haven't started depleting. We don't have a volume to average over because it's an infinite acting behavior, right? We can't average something we don't know the extent of. So we're just going to use initial pressure in the reservoir, okay? The initial pressure in the reservoir. And then we're going to have this PW. I'll go ahead and say the well's flowing since we got a rate over here, okay? And because it's now liquid, not gas, we don't have the gas equation. We're going to have the viscosity, which we assume is constant. The formation volume factor, which we're going to assume is constant. And then we're going to have, and I'm going to write it just like we were writing the pseudo steady state equation, except now I'm going to drop the 3/4 term. okay? Because I'm not using average pressure here. I'm using initial pressure. So I'm just going to write it like this. And you can actually use this equation to understand this infinite acting behavior. Because what you can do is you can say that, well, if I can track the distance here, if I know at a given time how far I am affecting, this threshold pressure drop. In other words, if I know this distance at a given time, then effectively this is my local RE at a given time. And it's just getting bigger. Okay? And bigger. At time 1, time 2, and time 3. Okay? Now exactly how fast that RE grows, we're not going to talk about yet. But conceptually you can see it. We're going to use the same equation, but we're just going to say at 1 hour I have a pseudo-steady state, kind of like I am draining this volume from this RE1 into the RW. Okay? So what we're going to do is that this is going to be changing because that is changing. Okay? This is a constant. We talked about this method of pressure transient analysis, PTA, being such that we set this as constant. And what's going to change, KH is constant, mu B, PI is constant, RW is constant. But the bottom flowing pressure, we know, will drop with time, PWF, from the initial pressure, and it's going to drop off and it'll look something like this. Okay? And the shape and magnitude of how that drops, the shape and the magnitude, how far it goes down, the shape and magnitude, are what allow us to find this permeability and skin. Okay? We can forget the skin because I've dropped the skin out of this. So I'm just going to say the permeability. So the shape and magnitude is going to give us what is the permeability. Okay? If we just have a single production drawdown, constant rate, and if we can figure out what the shape is and the magnitude is how far it's gone down, okay? And the shape is how fast it's going down. Okay? Then we're able to come up with the permeability of the rock. So this is a conceptual way of looking at the infinite acting period, is that it's really consisting of a drainage volume that just keeps getting bigger and bigger and bigger until you hit the wall. When you hit the wall, you have some physical boundary, okay? A true no-flow outer boundary, and at that point it stops, and you're not going to get gas or oil from the other side, okay? Now, this is a conceptual way to look at this infinite acting behavior. So the shape and the magnitude. Now, it ends up that if you, every well, no matter where you are in the world, okay, if you have a reservoir that's constant thickness, more or less constant permeability, you drill a well into it, okay, and start producing at a constant rate. Every well in the world will have the same shape of pressure drawdown. Okay? Is that right, Hamid? Doesn't sound right. He says something's wrong here. You're tricking me. Okay? But in fact, they will have the same shape. And that's what we're going to talk about. There's a general description of how the pressure should drop with time that applies to every such well in the infinite acting period. Okay? That's what we're going to talk about next. Okay? So it ends up that every well with, basically that being constant, that being constant. Of course, you've got a lot of assumptions. Low and constant compressibility with all of these assumptions, but, basically this radial, cylindrical, all these assumptions. If they're not violated, you can go any well in the world and it will have the same shape of pressure drop, which I'm going to call Pi minus PWF. That's going to be defined as delta P. Okay? Same shape. Hamid's not sure I'm right. He's going to go back to Chris, his advisor, and say, Curtis doesn't know what the hell he's talking about. But it's true. And what is that shape? Okay? Well, I'm going to show you that shape. Right here. Time and delta P. And I'm going to put it on a log scale. Okay? So just realize that this is on a log scale. Now this is, got to get the same. Okay? So it's on a log scale, and it's going to look something like this. And then I'm going to put a little line there. One line there. And it's going to go like that. Every well is going to look just like that. And in this early time period, because this is increasing time, in the early time period here, the slope of this is on a log-log plot is going to be 1/2. Okay, that looks like 1/3, but it's going to be 1/2. And how many know what 1/2 slope means on this plot? I know Hamid does, but anybody else? It means that the flow geometry is linear. Linear flow geometry. It means all the flow is behaving like it's just a linear flow. So we're just going to put L for linear. And then out here, it's going to follow it's going to be basically this delta P is going to be proportional with the natural log of time out here. And then that's describing what we call full radial flow. Okay, so you start getting flow regimes that you're seeing this radial going out. And this is what I'm going to call T for transition. Not transient, but transition. Linear, transition, and radial. And the greatest mathematicians who study the differential equation of this particular problem, of a well producing at a constant rate from a wellbore or W in Brazil, they taught you this, right? Yeah. Okay? That you get this solution. Any good mathematician, but they have to be pretty good, will get this solution. Now, unfortunately, this is not the solution we teach at the university. Most universities don't teach this solution, but the first one I believe to come up with this was Van Everdingen. Van Everdingen. You had, remember Van der Waals? All the good things come with a van. Van Everdingen, Everdingen, and Hurst, who worked together for some years before they divorced, unfortunately, to never speak again, as I understand. And I don't remember what year it was. 40s, 50s, something like that. 40s probably. They came up with this solution. And it's like this infinite summation of Bessel functions and all sorts of complicated things. It's hard to calculate, but this is what they come up with. Now, what we teach at the university, most places, I'm sure in Brazil as well, what they teach, I'm sure in Calgary, is not this picture. Now tell me how I should change this picture, Hamid. Yeah. We have they call it the exponential integral. The exponential integral solution. And it comes down somewhere like this. Okay? This is called the exponential integral solution. Which is correct only if your wellbore dimension is what? 0. How are we going to produce the oil out of a well with 0 wellbore radius? Hamid.
Infinite gradient pressure.
Yeah, we're not going to, is what he's saying. We're not going to. There are no wells with 0 wellbore radius, period. They don't exist. Okay? So if you take into account in the mathematics, and it makes it a lot more complicated because any yahoo, your grandmother, granddaughter, whatever it is, can figure out the exponential solution using a Boltzmann transformation or something. Maybe not your granddaughter, but okay, it's easy mathematics. But if you take into account the wellbore volume, the wellbore itself, then you get this linear transition, and this stuff is complicated in the mathematics. But it actually, that's a very simple proportional. Delta P here is proportional with the square root of time. Very simple. So the short. How can a radial well like this, how can it be linear flow? This is like cylindrical flow. Okay? Well, because if you look at the wellbore radius like that, you probably should look at it even. If we blow up the wellbore radius there, RW, and you look at the time where we're only draining from right here, okay, from just a little bit away from the wellbore radius. In other words, our local RE over RW is just slightly greater than 1. Then it's linear flow. You may not see it, but it is. Okay? Essentially linear flow. And that is the asymptotic solution at 0 time. It's linear flow. Square root of time, linear flow. And I wish people like who are the front of figure of teaching and our, I wish people like Tom Blassingame and other people teaching this subject would teach this. Because this is the actual solution and not the exponential solution. The only time you use the exponential solution is if you're doing interference testing. I'm not going to get into that. So, why do I say it's the same shape? Well, it ends up as the same shape. This is the mathematics of it, okay? The shape will always look like this. Now, what I'm going to do is I'm going to take a couple of example fields. I'm going to take in Oklahoma City. That's where I'm from. And then, since we have our guest, Hamid, where are you from? Where? Your town.
Shiraz.
Shiraz. Okay. Okay, and our lady from I'll give you pink, even if you don't like it, from Brazil. Where are you from?
Victoria.
How do you spell it?
V-I-T.
B?
V.
V is in Victor. Okay, just a second.
Exactly this, but
V-I-T-O
T-O-R-I-A.
R-I-A?
Yeah.
Victoria.
Yeah.
You got to learn to speak Okie. Okay, Victoria. All right, thanks. Sorry about that. Okay, so why do we have the same shape? Now, what I'm going to do is I'm going to plot my data from my well in Oklahoma City. The Oklahoma City field is about 600 million barrels. Okay, it's not a big field. And I'm going to say that at 1 hour, I'm going to go in and measure my well pressure drop. Okay, at 1 hour, and it's going to be right here. Okay, that's the first point at 1 hour. And then all of the other points are going to fall on that trend like that. Okay? And Hamid, he's looking at a field somewhere, and it's a real low permeability thing. Okay? Real low permeability. And his first hour is going to be down here. Okay? But you make your measurements and you keep making the measurements and you see that they're falling on top of mine. But you know, this, it might take a lot longer to get there, but it's going to cross mine and come up on there. Okay? And then, what was your name?
Talita.
Talita. All right, close enough. So you're out here. You got this wonderful high perm thing in Brazil somewhere, and your 1 hour is right here. Hamid's was down here, and hers is here, and the data all are going to fall like that. We agree if it looks like that, they all have the same shape, but they are at a particular point in the shape, square root of time, logarithm of time, transition, at different points in time, right? Okay? The transition from transition to at this point here occurs for my well after 2 hours. In Brazil, it's at 30 seconds. Okay, and Hamid's, it happens at 1 month. But that same point on the curve where the shape is the same, that means the derivative is the same, is right there. But it happens at different times. My pressure drop might be 100 psi, your pressure drop might be 1,000 psi, and her pressure drop might be 1 psi at that particular time. But the shape is the same. Okay? And how can we represent everything on one curve? And I'll tell you how. Because when we take our data, we don't plot delta P and T. We plot delta P times the following. We plot delta P times KH over mu B and rate. Okay? So I take my rate, my mu, my B, my KH, and I convert the delta P's into this quantity here. So times KH over Q U mu B. Okay? You do the same. You've got your own rates. I don't care what they are, mu B and so forth. And the lady in the back, she does the same. Now, on the time part, we have to multiply the time by permeability and divide it by porosity, viscosity, total compressibility, and the well size squared. The radius of the well squared. I drill this size hole, you drill bigger, she drills a small one. Whatever, doesn't matter. We have to use the correct RW. permeability, porosity, viscosity, and compressibility. If we do that, instead of using the actual time and the actual delta P, all of our data from our 3 different wells around the world will fall on the same plot, on the same shape. Okay? That's how it works. And this curve here is called, this is defined as dimensionless pressure. It's just a definition, that collection of terms. The mathematician and the physicist will explain that if you look at the differential equation, those terms all group together. So the well doesn't care if the Q mu B is, if that value is 100, or the KH over Q mu B is 100, it doesn't matter how it gets to be 100. Okay? Doesn't care what combination of K, H, Q, mu, and B. Doesn't care how you get that number 100, but if it's 100, then if I have 100 and you have 100, we have the same well, in a sense, in terms of this. It's called a dimensionless pressure. Okay? Dimensionless pressure. And I learned this dimensionless pressure, and it's strange because that's what we called it. In the books here, by the way, you guys may not get a break, because once I get started, this is the only time I get to teach well testing is these 3 hours. Okay? These are the books that I learned well testing in and all this stuff. This one is the first one, Matthews and Russell. It was a little too theoretical for me. And then this guy, Robert Erlager. You can see it's pretty well used. I'll pass them around. These are 2 of the books, early books on well testing. It's actually a dimensionless pressure drop. Okay, so I learned that later. But it's a dimensionless pressure drop, not dimensional. We call it dimensionless pressure, but it's a dimensionless pressure drop. And by the way, the well testing courses that I had, I was at Stanford. It was the mecca of well testing back when I was there. Henry Ramey was at the top of the Bill Brigham, Raj Raghavan, Cinco Lee. If I forget somebody and it's recorded, they're going to get me in trouble. Greengarten? Huh? Roland Horn, he's still there. He's the only one left. Okay.
John Lee.
Well, he doesn't like me anyway. So what?
John Lee.
John Lee. Well, he's not Stanford, but he's at Texas. But at Stanford there was this like mecca of things, and I took my graduate course from who? The PVT guy, Ms. Standing. I took the undergraduate from one of the gurus, and then Standing. Why did they have Standing, the PVT guru, teaching the graduate course in well testing? Because the professors were all out busy and being famous well testing guys. Nobody was around that semester, so they said, Standing, can you teach the graduate well testing course? And Standing, being he could do anything, kind of, if he put his mind to it, said, yeah, I'll do it. I'll go back and take a calculus course at the local junior college. Literally, he did that. And he taught the advanced well testing course at Stanford okay. So this is called dimensionless pressure. And down here, this is called dimensionless time. And it is, in fact, dimensionless. Okay? And that's why I say the shape is the same for all wells. Okay? In this infinite acting period. Even for a radial well. Now, interestingly, the wells we drill today, which are fractured, most of them, low perm at least, they're vertically fractured. You go in and you frac them, you know what you're not supposed to do. For environmental reasons, you frac them, create fractures. Well, a fracture creates linear flow. You can see the linear flow. You know, you got this big surface fracture, and the reservoir flow is linear into the surface, has exactly the same shape. Okay? Interestingly, if you drill a well, this is the top view, okay, and you put a fracture, vertical fracture like that, and then you got another well over here like that. So our no flow boundary is here, okay, something like that. Well, the flow into this well is coming where? Well, it's going to be coming like that. All right? Now that, if you have this kind of flow geometry, it'll end up being linear for forever, okay? This would be linear flow forever. So it would stay on this line here, in a sense, forever. But if you put in an unconfined area, if you just put a single well like that, in an infinite reservoir, which is what we're talking about, what we're going to get is flow that's linear in the beginning, right, like that. Okay. Now we've got this infinite reservoir, and then gradually, as the local area, what it's draining from, the ripple, you know, it's kind of like you don't throw a rock in, you throw a pole in, a javelin. You throw the javelin into the pond, and it hits, okay? And so the ripple effect is going to be looking like this, okay? Because you're going to get flow from here also, right? But then what's going to eventually happen is that this drainage shape is going to look more and more relative to the fracture. It's going to look more and more like a radial. Okay? It won't know after a while. If you throw a javelin into the ocean, you know, the original ripples will look right around the javelin. But if you're way up in the sky, God looking down, you'll see that ripple gets more and more circular. So it's going to, the shape of the delta P versus time is going to be just like this. Strangely enough. I mean, not exactly. But it's going to have the linear flow, finally the radial flow, and a transition in between. Okay? TD. That's what this is called. Dimensionless time. There's a constant for unit's sake. If you have units, you have to have, you know, there's a number in there. So we've got the definition of dimensionless time, dimensionless pressure. We've got the concept of linear flow, radial flow, transition from linear to radial. Let's see, what else are we missing? This is for a well producing at a constant rate. You're looking at how the pressure changes, or the pressure drop changes with time. Anybody who has had well testing, have I made any mistakes yet? Okay? You know, because I don't teach this very often, I don't get to think about it. This is basically the ABCs of well testing. Okay? A pressure transient analysis. But we don't sell pressure, we sell rate. And I told you last week, our main job as petroleum engineers is to do what? Ahmed, listen to them talk now. What is our main job as petroleum engineers? Production, forecast. All right, she gets you're going to win that Excel thing regardless. Production forecasting, rate versus time. Okay, and so we want to look at now. I will give you one break during the 3 hours, only one though. Okay. Okay. We're going to look at the situation where instead of imposing on our well a constant rate, we're going to impose on our wells a constant bottom-hole flowing pressure. Okay? Differential equations are the same. Okay? But now we're going to assume that the bottom-hole flowing pressure is constant. Okay? Instead of rate. Okay, we're still talking about infinite acting flow. Okay? For now. Infinite acting flow. And this discipline in reservoir engineering, production reservoir engineering, is not called pressure transient analysis. It's called DCA. Okay? DCA. Decline curve analysis. Okay? Decline curve analysis. And in connection with this, the guy who introduced decline curve analysis to our industry no. He treated boundary-dominated pseudo-steady state. The guy who introduced us to decline curve analysis of the infinite acting period was Michael Fetkovich. Same guy that's writing this paper that you've been reading. Okay? Mike Fetkovich. Okay, so the father is Mike J. Fetkovich. Just as in the pressure transient analysis, I don't know exactly who you want to call the father. Probably Hank Ramey is the proper. And by the way, Hank Ramey was on the committee together with one of his students, Raj Raghavan, on the doctoral committee of Mike Fetkovich when he got his Doctor of Technology degree here in Trondheim. As an adult 50 years old. He basically took a collection of his publications, which was and Hank Ramey, basically you have all of the first and second generation pressure transient students, most of them coming from Ramey. Brigham was his colleague, and so forth. So what's decline curve analysis? We want to know how rate varies with time. We're going to write the same equation that we wrote before, but now PWF is constant. And we've got the same thing, mu b, and we've got log RE RW, and we're going to give the same physical analogy that I talked about throwing the stone in the pond, the ripple increasing in size, the drainage volume increasing in time. And it is exactly the same RE time function that you can use here. Well, I say exactly. I'm sure Raghavan or somebody will show me that there's some different terms in this infinite summation, but within almost line thickness, it's the same RE versus time function. So you can use exactly the same, in a sense, logic or way forth, and I could take my Oklahoma City well, and now I put it on a constant bottom hole flowing pressure. You take your well, put it on a different bottom hole flowing pressure. She takes her well, puts it on a different bottom hole flowing pressure, and we all go in and make a plot of rate versus time, again with a log scale. Now we're plotting rate. And what is it going to look like? It's going to look like that. Okay? Again, this is not a very good. Slope of a half, or maybe it's 2 when you turn it upside down. Square root of, basically Q is proportional with 1 over square root of time. Q is proportional with 1 over log t. linear flow, radial flow, transition flow. I put in my data, rate time. This is 1 day, like that. Hamid puts in his 1 day. They cross, and I still can't get her name right, but Brazil, 1 day, and her data looks like that, much flatter. Hamid's data looks like it's losing a lot more rate than mine, and mine's losing rate faster than hers, if you just look at it. But if instead of plotting just rate, okay, if I plot KH delta P over mu B, like that, and we use the same multiplier here, times K over phi mu C RW squared. So if each one of us take our data and add this constant onto it, then all of those data will fall on the same trend, the same shape curve. And this is called QD, dimensionless rate, and this is our same dimensionless time. Okay? There's a lot of Russians doing stuff that we don't know about, okay, who did things and published in Russian we didn't know about, also in China as well. But there was one of the Russians, her name was Streltsova, I think. I was talking about her last week at the big conference we had. And the new president of the SPE is a Norwegian guy, Helge Halderson, vice president of Statoil. And the one who'll be after him is Nathan Mayhem, who I knew from Stanford. And he was kind of a well testing guy. We were trying to remember, because we programmed her solution to the partial penetration. Her name was Streltsova. Anyway, QD, TD. And it was a Russian, Sadovich, I don't probably spell it right, Sadovich, something like that, who did this solution first. I'm not spelling it right, but something like that. And for practical purposes, QD as a function of TD, infinite acting for radial well, is for practical purposes equal to the inverse of the PD for infinite acting. Okay? Almost line thickness. Not exactly, but almost. Some different terms in the infinite series, but you learned that right. Also? Okay. How about you in the back from Brazil, young lady? Did you learn that in Brazil, that the dimensionless rate in infinite acting is approximately equal to the inverse of the dimensionless pressure? Anyway, it is for practical purposes. Okay? So, okay, what am I missing? I think this is basically it. So the one who introduced this was Mike Vetkovich, and in terms of taking, in fact, he took this solution, the tables from that, had the Russian article translated, it was a book, I think, had it translated, had the tables, and then used it to create dimensionless rate, dimensionless time curves, which was in his first paper on decline curve analysis around 1974, I think. And in that solution, and I do hope that Mr. Tom Blassingame hears this video at some point in time, in that solution is the square root of time and nothing else. The square root of time linear flow model is in the original work by Fetkovich. And in fact, it was emphasized in the 1970s when it came out, because that's when vertical well hydraulic fracturing started. In fact, Greengarten got his name started. He got his work started. It was Ragavon, Greengarten. We're all doing work on coming up with these analytical solutions for fractured wells. And Fetkovich was the one who observed that, in fact, the linear flow solution for the radial well was the same as the linear flow solution for the vertical fracture well, for practical purposes. Same solution could be used. And so what we can also say is that the dimensionless rate solution for is approximately the same for a radial well and a vertically fractured well. And a horizontal vertically fractured well is just the sum of a bunch of vertically fractured wells. Okay? Linear, transition, radial. Square root of time, logarithm of time, and then transition. That's it. So you don't have to learn a lot of new things, going from the old traditional wells, radial vertical wells, unfractured, to what we're doing today for practical purposes. So what we're going to do, we're going to take a break now, and after the break we'll come back and we'll talk about the transition from infinite acting into boundary dominated. Okay? We'll talk about that transition.